Okay. Very happy to have Sushil on the website. You can see, so he's the BTech from IIT Bombay in mechanical engineering. Then he went to do his master's in Georgia Tech. Was it in Noir?
In IE.
Yeah. And then he kind of liked it so much, he shifted to PhD program there. So he's doing the PhD in software research. Noir. He's in fifth year now. He's doing exciting work in applied probability, queuing and related areas. Today he will tell us about dynamic pricing and matching.
Thank you for that introduction. Thank you for coming to my talk. Really glad to be here. It's a very beautiful campus. So today I'll share a little bit of what I did during my PhD and what I've been doing during my PhD. Motivated by online marketplaces, we study how you would want to price and how you would want to manage in systems that relates to online marketplace. So this work is jointly by with several folks that I met during the course of my PhD. Pompovi, she was a student with me at Georgia Tech, and now she's a research scientist at Amazon. Hwang, he's a professor at Georgia Tech. Francisco, he's at UCLA, and Siva, he's my advisor, he's also at Georgia Tech. So with that, let's get into what the talk is about. This work is motivated by gig economy. As you might be aware, in the past several years, there has been an accelerated adoption of gig economy in our day-to-day lives. For example, $204 billion revenue was generated just in 2018. On top of it, 36% of the workers in the US joined gig economy. Right, gig economy, essentially, you can think of it as online marketplaces. So let me give you some examples, like essentially ride-hailing platforms, meal delivery services, bread and breakfast, package delivery, freelancing, and many more. Essentially, any service where you do crowdsourcing from one side and try to provide some services on the other side. That's essentially what gig economy is.
And this $104 billion is just MasterCard or it's overall?
Oh, MasterCard is just a reference, but this is overall.
Not that big. Maybe it's much bigger already now.
Yeah, maybe like because 2018 it's been growing, so yeah. But this number is definitely very big because like join in one way or the other. So in terms of freelancing, you would in your downtime you might become an Uber driver and then complete some rides. So the good thing about it is flexibility, that you can join at any point of time and then you can stop working whenever you want. And that kind of one really reason of its adoption, and that's getting adopted more and more often. So motivated by this, we want to understand how to operate such kind of platforms. At least give some benchmarks and give some guidelines to a service provider. So yeah,
Amazon is $500-600 billion revenue and much bigger than this. But nonetheless, 36% of workers is very impressive.
Yeah, right. Good. Thanks. All right then. Essentially, for a system operator who's managing such kind of a platform, you might see majorly two challenges. So the first one would be a disparity in supply and demand. That means you might have too many buyers but too few suppliers, and you don't want to have such kind of a situation, because again, if you have too many buyers, then there's no seller to sell, and people will be unhappy. The second major challenge is you might have enough buyers and enough suppliers, but the buyer is not wanting to buy what the supplier is selling. So there's a misalignment in their preferences. And that's why you cannot really match those buyer and supplier to each other. And that's the misalignment in supply and demand. Again, such kind of a scenario, you don't want it to happen. So these two major challenges, first one we solved by dynamic pricing, tackled by dynamic pricing. So essentially, Again, if you have too many buyers, you want to do some kind of a surge pricing, you want to increase the price for the buyers so that not too many buyers join the system in the future, and the system is then pulled back towards equilibrium. For the second one, we solve it by doing smart matching. So you want to do matching decisions in such a way that this misalignment doesn't happen as often. So because matching decisions right now is going to affect what your system is going to look like in the future. So you want to match in such a way that this misalignment happens as less as possible. So with that, let's make it a little bit more concrete. So what we do is we take a stochastic network viewpoint. This has mainly three salient features. The first one is types. So essentially you have multiple types of customers, and again for buyers I'm gonna call them customers, and for sellers I'm gonna call them servers. So one example is ride hailing, and that's why we have servers denoted by cars. So the first salient feature is type. So there can be multiple types of customers and multiple types of servers. In the application of ride hailing, you can think of dividing the city into different parts, and each geographical location is a type of a customer, and each geographical location is also a type of a server. Now, the second salient feature is compatibility. So if a customer and server's location are close to each other, so the proximity is there, then they will be compatible to each other. Otherwise, they're not compatible to each other. So a bipartite graph essentially is given to you. And the third salient feature is matching. So if a customer and server is compatible, and you have a customer and server waiting in the system, then you can decide to match them. And as soon as you match them, they depart from the system instantaneously. Under this setting, our objective is to set prices for all types of customers and all types of servers and perform matchings in such a way that you maximize the profit for the system operator while minimizing the delay experienced by the customers and the servers. So that's an overview of the model, but I have not specified all the details yet. Because this is a stylized model, I just want to mention that there are many applications of such a stylized model, and it's not really limited to ride hailing. So again, the first one, as I already mentioned, the application is ride hailing, but you can go beyond that and use such kind of models for modeling various scenarios, various different applications like payment channel networks, where you will have a two-sided payment channel network where A wants to send money to B and B wants to send money to A. Again, we'll not go into much of the detail. Again, many different applications like quantum networks as well. Again, if you're interested, we can talk more about these offline, but here just what I wanted to mention was there are several different applications, and because this is a stylized model, you can say many things about beyond ride hailing as well. Now with that, let's start with the simplest case. So you have a single type of a customer and a single type of a server. The customer arrives with the rate lambda and the servers arrive with the rate mu. Then the first question that you would ask is, when is this system stable? So in the long term, you want the system to behave more or less in a nice fashion, like nothing should blow up, should go to infinity as time goes on. So with that, again, if lambda is greater than mu, then you would expect the customer queue to blow up. If mu is less than lambda, I mean, if the other case, if lambda is less than mu, then you would expect the server queue to blow up. So again, both the cases where lambda is greater than mu or less than mu will not give you a well-behaved system. The only case that remains is lambda is equal to mu. So this is like balancing on a pinpoint. In this scenario also, it doesn't behave very well because the underlying Markov chain would just be a random walk, and you would have a null recurrent random walk, and it doesn't really scale well because if you have a three-dimensional random walk, then you will just have a transient system. So what this means is that whatever values of lambda and mu you set here, you will never be able to stabilize the system. And that's why you need to do something else on top of it to be able to gain stability. One way to do it is essentially we need external control to make the system stable, as in we want to change something in the system so that we drive the system towards equilibrium again. One way to do it is by dynamic pricing. So you change the arrival rate of the customer and server based on the queue length that you see. So essentially, if your customer queue is too long, then you increase the price for the customer, and that's going to reduce the arrival rate for the customer. Because of that, you will push your system back towards stability. And similarly, when you have too many servers in the system, you want to again decrease the price that you're offering to them. And that's again going to reduce the arrival rate of the server, and that's going to push your system back towards stability. So by doing dynamic pricing, one can essentially make the system stable. And thus we can analyze such a system in steady state. Any questions here?
So how do you use this as a three-dimensional random walk? And what's the random?
Right. Essentially, what I was mentioning is if you have three of these, like three types of customer, three types of server, and a one-to-one compatibility, then you would have a three-dimensional random walk, and that will be transient. The underlying Markov chain will be transient. So it doesn't really scale well, and if you have multiple types, then you might see system that is even transient and not even null recurrent.
But even if you have this one type of customer and one type of vehicle, you're doing a simple random walk on the real line.
Real line, yeah.
So then even that grows as root n as
Correct. So it's null recurrent. I mean, it's not transient, it's null recurrent, it's slightly better than transient. But I'm saying even that is not very good because it doesn't even scale well. It doesn't stay null recurrent. It can become transient as well. So you want something to be positive recurrent. That's essentially what I'm motivating here. That you would want to make the system behave such that the underlying Markov chain is positive.
And now, so you're suggesting that, when you think of blowing up, you can either play with the lambda rate or you can play with the mu rate. So you give us insights as to what is a better thing to do when.
So in this work, the policies that we use are pretty much symmetric in terms of lambda and mu. But it turns out that you can fix one of them and just vary the other one and still get stability.
No, but you can imagine can one give just realistic setting, maybe at Mumbai airport, the better thing to do is this and not that.
Right.
Because of the issues with that.
Right. I think I don't have insights on that, but I think that's a good question. Like we have some of follow-up work where we do some strategic behaviors for the servers. In that case, we show that by doing dynamic, depending on the system parameters, by doing dynamic pricing just for the server, might give you a better profit. But again, that's really modeling something that's very specific. So I think the model that we are considering, it really doesn't matter.
Right.
But maybe if you add more features into it, you might see one is better.
If you make it kind of more realistic, like the customers have a choice to go by other vehicles. Or the Uber people, the driver, I don't know what their constraints are, but they are thinking so very.
Right. Maybe the customers don't like volatility. Then in that case, you might want to have a static price for the customers and do dynamic for the servers.
Right.
In some cases, servers may want to set their own prices. They may not like volatility. In that case, maybe you want to do the other way. Yeah, that's a good question. Thanks. Any other thoughts? All right, let's move on. So this is just an overview of the simplest case and the technical challenges we face, and by doing dynamic pricing, we can get over the technical challenge. We can make the system stable and thus analyze it in steady state. So before going into the details, just a quick literature review of what's out there. So there's a lot of papers out there, a lot of work relating to these matching queues, two-sided queues. There are a lot of different names, but they all mean really a very similar model, but some things are different in different models. One salient feature of all these models is if a model is inherently unstable, then people have analyzed it in transients. Because it's inherently unstable, then they don't do any kind of external control to make it stable, rather than analyze it in transients. Here, we are doing a steady state. There's some papers that are doing steady state as well, but we do a more fine-tuned analysis. So just a quick distinction of how this paper stands in the literature. Now with that, let me just quickly give you an overview of what's coming up. So because it's a 1 hour talk, so I don't want anybody to get lost. So the talk is divided mainly into two parts. The first one, I talk about this paper where essentially the punchline is that we propose a near optimal pricing and matching policy. That's essentially what we want to do, that we want to propose a pricing and matching policy that gives you the desired profit or a profit that's as close to optimal as possible. Again, with some rate of convergence to the fluid. Again, I don't want you to really think too much about it, just giving some kind of a preview of what's coming up. Then the second one is based on, again, this paper. Here the punchline is we analyze the canonical setting of a single linked two-sided queue where you have a single type of customer and a server, and under a general class of pricing policies, we are able to show the distribution of what the queue length looks like. And again, the punchline is that we see a phase transition for the limiting distribution of the queue length, unlike classical queues. So again, that's something that's interesting and that's coming up. Again, I'm not defining a lot of the things that are there in this slide, but just giving a preview of what's coming up.
Now, this year that you showed in the previous slide, it's all for steady state views.
No, most of them is for transient actually. A lot of them is for transient. Because again, because of the inherent instability, either people impose more assumptions to make it stable or analyze it in time. So with that, we'll start with the part one. Again, which makes sense. So then here's the model. You have a bipartite graph. You have different types of customers, different types of servers, and a compatibility graph between them that's given to you. The dynamics is as follows: that first, the system operator is going to set the price for all types of customers, all types of servers. Based on the price, there are arrivals. The arrivals are essentially Poisson prescribed with the prescribed arrival rate. So once you set the price, you know the arrival rate. And once you know the arrival rate, there will be arrivals which will be just Poisson with the prescribed arrival rates. And once there are arrivals in the system, then the system operator will decide the service. Essentially, it will decide which of the pairs to match. So if a customer and servers are compatible to each other, the system operator can decide to match them or can also decide to not match them. But depending on what the system operator decides, those pairs will then just leave the system immediately. And this dynamics gives you a continuous time markup. And under this TMC, our objective is as follows. So there are again many terms here. I'll go through each of them one by one. The first one is the revenue that you get from the customers. So again, lambda j is the quantity of customers that are coming into the system, and fj is the inverse demand curve. So that's a one-to-one mapping between price and quantity. So fj essentially gives you the price that you're setting for the customer. So price times quantity is just the revenue. Again, similarly, price times quantity is going to be the cost that you are paying to the servers. Because you are paying to the servers, you are taking from the customers. And finally, we have a weighting penalty, which is basically the queue lengths here. You want the queue lengths to be small because you want the customer and servers to have a good experience. That means to experience lower waiting times. And this is how we characterize. And under conditions that you have a feasible matching, that you only match a customer and server if they are compatible to each other. And the underlying system that you get is stable. The underlying CTMC is for it.
So this is one time point or it is a steady state?
Yeah, it's a steady state. So it's maximized over the expectation. Expectation is taken over the steady state. And the constraint is that whatever pricing and matching policy you use, the underlying CTMC should be stable. That means the steady state is very so this is the objective that again we want to maximize. So come up with a pricing and matching policy that maximizes this net profit.
But the steady state, so the body steady state will be achieved in small time.
I mean, I guess we don't talk about mixing times. Is that what you're asking about?
Yeah, as in like so there should be so there should be at least some kind of like you're not in some boundary case where you will just not hit this.
Right. Yeah.
That is probably
correct. I mean, I don't know if it's like exponentially ergodic in this case, but probably would be. And I guess like we consider asymptotic regimes. If you are very close to the asymptotes, then it's going to converge very, very slowly. But if you look at the pre-limit, then it's going to be, I mean, in the simulations, you see that it takes like a million time steps to a million transitions to be able to, which is
like we should still some number.
correct. It would scale with the number of links. We do not have like the equation, like the theorem that gives you the mixing time, but
Yes.
So you'll assume that you know these curves?
correct. That's a good question. So these curves.
This is the control. This is how you describe it.
So these are supply and demand curves.
Then when you set price Q or so what's lambda Q?
Correct. Depending on the correct. Here's the state of the system. Depending on the state of the system, you set a price. And then so here I'm doing like change of variables here, because depending on the state of the system, you set the price, and then depending on the price, you get the arrival rate. But here I'm just keeping the price part here because I'm assuming that the policy that you are using is just Markovian. So depending on the state, you set a price, which gives you an arrival rate. So I'm just skipping the price going to the arrival rate. And the good thing is that if you look at it from an arrival rate point of view, you get a convex optimization problem. Otherwise, you do not. So that's something that's standard in revenue management, that you want to look something from a quantity point of view rather than the price point of view.
But nonetheless, we're saying that given a state, if I set a price, I know what my rate is.
Correct. Yeah,
You're not letting that either.
yeah, exactly. Yeah, that's determined by this curve essentially.
That's follows.
Yeah, so essentially we are assuming these curves are wrong. And again, that begs the question whether if you can then come up with a learning policy on top of all of this that on the fly learns the curves and then set the prices. All right, so moving on. So essentially, this problem again, if you just look at it, just glance at it, it seems like a complicated optimization problem because you have expectation that's taken over steady state or over CTMC, which again, very in a complicated manner depends on what pricing policy and what matching policy you fix. So again, this is fairly intractable, and that's why what we do is we first relax some of these things and come up with a first order approximation, which is just a fluid model. To do that, essentially, you replace all the stochastic quantities by the deterministic counterparts. So here, all the expectations are gone, all the Q lengths are gone. Yes.
The question, like, so what does the Markov chain look like here? Like, what are the states?
Correct. Good question. The states are essentially the Q lengths. So the Q lengths of all the types of customers, all the types of servers. That's going to be your state. Depending on the state, you fix a policy. I mean, you fix a policy, so you, depending on the state, you know what the arrival rates of the customer and service are going to be. Then you know the arrivals are going to be Poisson based on that. So then you essentially have a queue that's evolving with time. So it's a queuing model because everything is exponential and Poisson, you get a sequence. Does that answer the question? Yeah. Okay. So again, because the previous optimization problem was pretty involved, we come up with the first order approximation of it, where we just replace all the stochastic quantities by the deterministic counterparts. So all the expectation is gone, all the Q lengths are gone. Lambda JQ is then just replaced by lambda J, and again same for mu. So you get again maximizing profit, revenue minus cost, subject to these balance equations. So to understand the balance equations, you can think of it as a fluid, essentially literally fluid model, where fluid is flowing from the left hand side, and then you have valves here where you can decide how much of the fluid to send here and how much of the fluid to send here. And you want to do that while ensuring that these equal to lambda and these are equal to mu. So you want to come up with the chi's. Chi's are the matching rates. So chi ij is the rate of matching of I type of server with j type of customer. You want to match it in such a way that you do not violate any compatibility constraints, and also you match all the incoming customer arrival rate with the server arrival rate. So these are just balanced equations. So again, we have come up with an optimization problem. The first thing we want to do is we want to relate this optimization problem to the one which we had in the previous slide.
So like, I guess, so they depend on the state, right? The lambda J's and the mu I's.
Correct, but in this, I'm just ignoring all of that. Just saying that Q, there's no Q's. Everything is a fluid, so there's no Q's at all. And lambda J Q can be thought of as a stochastic quantity. I'm just replacing it with its expectation in some sense. So lambda J can be thought of as expectation of lambda J. You can think of it like that.
In the fluid setting, there are no Q's.
Okay. In the fluid setting, it's just so fluid setting is like a deterministic counterpart. So if you have a single link to set it, exactly one customer arrives, exactly one server arrives, then you will never see a queue.
Right. Again, this can be, so this balancing can be achieved in a variety of different ways, right? Depending on what I guess price you're charging the arrival and what you're paying the
Correct.
servers.
Correct.
So how do you capture the fact that there are all these options available to you?
Right. So again, this will give you all the possible feasible options, and then you want to pick that option that maximizes the profit.
Right, so lambda J and mu I are still variables.
Correct. Correct. Yeah. The maximization is over lambda, mu, and chi. Good. So again, we've come up with this simpler optimization problem, but we want to relate this optimization problem to the one which we had before, which was more complicated. And that's what we do next. Essentially, what we prove is that this, if you solve this fluid model, then it's going to give you an upper bound on the achievable profit under any pricing and matching policy. So again, this is going to give you a benchmark. Now, once you have a benchmark and an upper bound, the first natural question to ask is, can you achieve this upper bound?
The other term went away, the waiting penalty.
Correct. The Q terms went away because again, in the fluid model, there's no Q's at
There's
all.
no waiting.
There's no Q's at all. Because everything is deterministic, so you don't see any Q's at all. Again, the way to think about it is if you have one type of customer, one type of server, if the arrivals are exactly lambda on both sides, then you never see it. So with that, the first question you would ask is, can we achieve this this upper bound? Because once we come with an upper bound, that's the first natural question you would ask. And the answer to that is no, because again, you are ignoring the Q-length terms here, the weighting penalty terms. That's not taken into account at all, and that's the reason you will not be able to achieve this upper bound exactly. Then the second question you might ask is, if you can't achieve it exactly, can we achieve it in an asymptotic regime? And that's the rest of the talk, essentially. So what we do is we first define a large scale regime. So we scale all the arrival rates by a factor eta and analyze the system as eta goes to infinity. So essentially, you can think of it as market is becoming larger and larger. You have a more supply of customer and server, and then both of them are scaled by eta. Now with this large scale regime, what we want to analyze is the profit loss. So for the eta system, the profit is just going to scale with eta. So eta times gamma star minus the profit under a given policy. So this is what you want to analyze and minimize essentially, because we want to maximize our eta. You have any question? Yeah, good. So that's what we want to analyze. Now, what we do is we analyze two pricing policies and two matching policies. That gives you 4 different combinations. So the first pricing policy that we consider is static price. So for any given type of customer, this is the Q length. You set the fluid optimal price until a threshold. Outside the threshold, you don't allow anybody to enter the system, and that's going to ensure your system is going to be stable. And you want to mimic the fluid solution. That's why you're using the fluid solution. The second policy we use is the generalization of this, which is 2 price policy, where again, until a threshold, you use the fluid optimal prices. And after the threshold, you reduce the arrival rate by a factor epsilon. And again, that's going to ensure that your system is stable. So you have 2 parameters here that you can optimize. The 2 matching policies we use is, the first one is random matching. So random matching again tries to mimic what the fluid model is doing. So what it does is, if a customer arrives of a given type, then it is matched to a compatible server proportional with a probability proportional to the fluid solution. So it is then trying to mimic what the fluid solution is doing. Because fluid solution gives you the optimal matching rates. And the second policy we use is max weight. So max weight again ignores what the fluid solution says, and what it does is, if a customer of a specific type arrives, you match it to a compatible server that has the longest queue. So again, you want to bring your system back to zero as much as possible, and you do that by matching it to a compatible queue that is longest. So again, that will give you 4 different combinations of pricing and matching policy. We analyze the performance of all the 4 combinations, and this is what we get. That if you use static pricing, then under any matching policy, and any of the 2 matching policies, the profit loss will be of the order square root of eta. And this is going to be near optimal because the fluid scales with eta, and if the gap between them scales with square root of eta, then it's going to achieve the fluid profit as eta goes to infinity. And on top of it, if you go from static to 2 price, then the loss in profit actually reduces from square root of eta to eta to the power 1/3. That means by using dynamic pricing, you are able to improve the profit by a little bit. Now, another question to ask is it possible to improve this eta power 1/3 to even further? That is something.
Dynamic pricing, so what are the thresholds would they look like?
Correct. I'll come to that in after a couple of slides. I'll give you some intuition on how to set those thresholds. Then the question you would ask is, if you are eta per 1/3 for this 2 price policy, can you come up with a different pricing or a different matching policy and be able to improve over eta per 1/3? And the answer to that is pretty much no, that under a general class of pricing policies and under any matching policy, you cannot beat this eta per 1/3. So in some sense, 2 price policy is giving you the best possible profit loss.
So how does the epsilon eta scale with eta?
Correct. Yeah. So I'll come to that in a couple of slides. I'll give more intuition on what those are. So do hold on to that question. Just to give some insights on what this result is saying. The first one essentially says that by doing dynamic pricing, you can improve your profit loss from square root of eta to cube root of eta. So that gives you advantage of dynamic pricing. The second one is by just having a small amount of dynamic component is enough, because you cannot improve over eta per 1/3, and 2 price only has a small amount of dynamic component. So that's enough to give you most of the benefits, at least under this asymptotic regime. And the third one is the 2 price policy seems to be the primary driver of the reduction in the profit loss, because whatever matching policy you use, it really doesn't matter, you get the same profit loss. So then the question is, does it really make sense to use max weight over random or random over max weight? And that's what's coming up, the advantage of max weight in the large market regime. But before that, let me answer the question that came up. So how to set the threshold essentially for the 2 price policy, and where is this eta per 1/3 coming up? Because you might see square roots coming up here and there because of central limit theorem, but eta per 1/3 seems to be something that's little different, at least. So essentially here I have written down what my objective was. This is the profit loss. So this is the fluid profit minus the profit under a given policy plus the expected Q length. So this has 2 major components. The first one is I just call it the revenue loss, and the second one is expected Q length. Now we want to analyze both of these components. So consider a general pricing policy that is an epsilon perturbation of the fluid optimum, because we want to stay close to the fluid but still have a little bit perturbation around it. Now with that, what you can do is, let's say P is like the revenue loss. P is the revenue, then you are essentially setting X star plus epsilon as your price. Then by doing Taylor series, you get the following. The first term is essentially the fluid optimal term. The second term disappears because of the optimality of X star. And then what you get is the revenue losses of the order eta epsilon square. Now we want to also analyze the expected Q lengths. So it behaves like a single server queue in heavy traffic. Because you have like an epsilon drift that's pulling you back towards zero. Again, if you're not sure what that is, let's just take it for granted. that gives you the expected Q length to be of the order 1 over epsilon. Again, that kind of makes sense that if you increase epsilon, then your Q length should reduce because you're pulling your system back towards stability more and more. So the Q lengths are of the order 1 over epsilon. And then there's clearly a trade-off here. And to optimize the trade-off, you can pick epsilon to be just equalize these two, pick epsilon to be eta bar minus 1/3, and that gives you profit loss to be of the order eta. So essentially the threshold that you should pick, the perturbation that you should pick should be of the order eta bar minus. Such kind of a trade-off is more fundamental and doesn't really need this definition of asymptotic regime. Essentially, you can say that you can set a pricing policy, but impose this constraint that your expected Q length should be at most 1 over delta. Then we can show that under that policy, the profit cannot be more than the fluid optimal minus something that's of the order delta square. So the same trade-off appears here without even the definition of the asymptotic. So something like that, like this, is more fundamental to the system. So with that, let's go back to the question about why is max weight better than random. So let me give you a very simple example to just illustrate the point. Let's say we have these two graphs. So again, we want to quantify now the profit loss in terms of the number of types of customers and servers. First, we quantified it in terms of eta, which is the scaling factor with which your arrival rates are going to infinity. Now you want to quantify it in terms of the number of types. So let's take these two examples. The first one is n independent matching queues. So it's a very sparse graph. Then the question that I'm asking is what would be the profit loss here in terms of eta and also in terms of n? Does anybody want to take a guess what it would be in terms of n here, the profit loss? So for a single queue, it's eta per 1/3. So if you have n of these and n independent copies of these, it would just be n times eta per 1/3. So that's what you see, that if you have a very sparse graph, each one will have a profit loss of the order eta per 1/3. And because you have n of these, your total profit loss will be eta per 1/3 times n. Right? Now let's consider the other extreme where you have a complete graph. Here you can think of it as a one giant resource pooled matching queue with arrival rate n times eta. Now what would be the profit loss here in terms of n? Any guess? N eta, exactly. So it would just be eta per 1/3 times n to the power 1/3. Because it can be thought of as a giant single queue with arrival rate n times eta. Right? So now here what's happening is, depending on the underlying graph structure, you are getting different profit losses in terms of n. So then the goal is first to come up with the conditions on graph such that it behaves like a complete graph, but it's still much more sparser. And then once you come with the condition, then a policy that achieves such a resource pooling, that means you are able to get this n per 1, which is much better than n. So to resolve the first goal, what we do is we come up with a CRP condition, which is again very standard in the queuing literature. To gain intuition on what this is saying, this is very similar to a matching, false matching in a weighted graph, and it implies the
CRP resource pooling,
complete resource pooling. Complete resource pooling, because you want to have one big giant resource pooled component. So again, this is the condition which to get intuition, it's like a false condition on weighted graph. So like a perfect matching condition. To gain more intuition, the above condition implies that the graph is connected. That's something that you would want at least, right? If it is not connected, then bad things can happen. So you want the graph to be at least connected. On top of it, it gives you some more nice things about the graph. That the fluid solution is again interior of some stability region, which again, I'm not going into the details, but essentially if you have this CRP condition, you can have much sparser graph compared to a complete graph and still be able to have a complete resource pooling that is behaves like complete graph. Now under this CRP condition, what we want to do is we want to augment the results that we had before in terms of n. So essentially, if you use random matching, then we show that you can have loss as big as order n. But if you use match weight with static price, then you can get square root of n here. And if you use it with 2 price, then you get n to the power 1/3. And also, again, we can show a lower bound. That's again eta per 1/3, n per 1/3, which is again in line with the intuition that we had, that it's just a giant single set. So again, to get some intuition from these results, what these results are saying is that first match weight is better than random, because clearly you get a much smaller profit loss in terms of n, so it scales much better. If you have a large market, it's going to scale much better because it's exploiting the underlying network structure. The second one is match weight is optimal with respect to n because it matches the lower bound in terms of n as well. We show this by essentially showing a state space collapse. So essentially, we show that the system with a very high probability is such that there are either only customers waiting or only servers waiting in the system, not both of them at the same time. And that kind of resolves the question that we had at the start about disparity of supply and demand. And match weight is in some sense able to alleviate that problem that you have either only customers waiting or only servers waiting with a very high probability.
So a lot of people have not know max weight very well.
Right.
If you can max it also, let's say usual wise it can achieve this.
Right. Okay. So the definition of max weight is as follows: that if a customer arrives in the system, then the way you match it is that you look at all the compatible servers and then you match it to the server which has the longest queue. Right. So essentially, what max weight is trying to do is trying to equalize all the queues, because it's again matching to the one that is the longest. So the longest will become smaller. The smaller will become longer because the arrivals will happen to the smaller.
Stable situation, all the queues are about the same.
All the queues are about the same, right? And then if all the queues on the customer side are about the same, and if you have a connected graph, then again, what max weight is doing is, if you can match, you are matching. If there is any compatible server in the system, you will match it to that server. You are not having compatible customer server waiting in the system. Now, if all the customer queues are equal, then none of the server queues can be non-zero. Because if all the customer queues are equal and all of them are equal to 10, then you cannot have any of the server queues unequal. Because if there was any server queue that is unequal, you would have matched it already, because that's what max weight is doing. And by equalizing the queues on the customer side and server side, that's essentially what you're getting. That all the queues are becoming equal, and that's why you have only one side that is not equal. And that's how you're getting state space collapse. And that's going to help you, because now the system is looking like a single link to sanity. Because the only distinction between multiple types and a single type is that you might have customer and server both waiting at the same time and they are incompatible. But max weight is making sure that doesn't happen. And that is why you are getting optimal in terms of n. That it's behaving like a single link. And the third takeaway is that you need to do a joint optimization of a pricing and matching policy. Because if you fix a pricing policy but try to optimize over matching policy, you might get something suboptimal. Like if you fix a pricing policy but try to optimize over all matching policies, you might get something suboptimal. And similarly, if you fix a matching policy that is even optimal, you might get something suboptimal if you don't use the right one. So these are like, one is optimal, but the other one is not. And that's why you're not getting optimality in terms of either n, eta, or both. So a joint optimization is important. And with that, that completes the first part of the talk. The second part is much smaller. So the first part of the talk, we are able to set prices, perform matching, such that we are able to maximize profit at least near optimally and also minimize the delay. So any questions here? I'll stop for some questions about this part of the talk. Then we'll go to the next one.
So if you look at try to do a non-asymptotic analysis where you actually take the students into account also, what sort of complications are there?
Correct. So to answer part of the question, we are taking into account the QLMs in all the results. So all these results do take into account the expected Q length. And it's a stochastic model, so you do see Q lengths being non-zero. So that's already there in the analysis. Now to do non-asymptotic analysis where you get exact expressions, even for a finite eta, essentially that's the non-asymptotic analysis. So the good thing, the way asymptotic analysis helps us is that we can ignore all the lower order terms. So here there are many more terms which are lower order in terms of beta, and that's what we are ignoring here. To be able to do a non-asymptotic analysis, we would need to characterize all the terms essentially. So characterize everything exactly in terms of all the quantities, and that would require a more precise analysis essentially. So that's the challenge, yeah. But the Q lengths, we are taking into account the Q lengths here. Because that's exactly where the eta per 1/3 is coming from, the trade-off between the profit and the Q lengths. So the fluid model essentially just gave you, you can think of it as you have a very complicated optimization problem to start with. Then you relax it, come up with a fluid model, you solve it, then use the solution of that fluid model to come up with feasible solutions for your original problem. And then do analysis to show that the solution that you came up with for the original problem works well. That they are close to the best you can get.
So these lower bounds, they. So I guess you didn't speak about the lower bound at all. No?
Like I gave some intuition in terms of why this eta per 1/3 is something that's expected. Is because of the underlying trade-off between the profit and the Q lengths. And if you use any pricing policy that is an epsilon perturbation of the fluid, then you would see this eta epsilon squared time versus 1/epsilon trade-off. And you can only pick epsilon.
But can you use the fluid model for the lower bound though? Because it's probably not in steady state then.
Correct. So fluid model will not give you any of these bounds, right? Because these bounds are for the stochastic model, like the giant optimization problem that has expectation in it for. So all of these are for the stochastic model essentially. So this is telling you how far away from the fluid profit you are. Like fluid gives you an upper bound, and this result is telling you that if you use the fluid solution in your stochastic problem, then you will lose this much in compared to what your fluid would give. And because this is sublinear in terms of beta, the amount that you're losing is much smaller compared to what your fluid profit is, because it's scaling as order eta. So this is much smaller, and what that essentially is saying is that if your eta is large enough, then you are essentially mimicking the fluid model good enough, and you are able to achieve the profit that is much closer to the fluid model. So by solving a simpler problem, that is the fluid problem, you are able to get feasible solutions for your stochastic problem that is near optimal. Any more questions on this part of the talk? So with that, let me just briefly mention what other things that you can do here. Until now, we only cared about the expectation of the Q lengths. Now one can analyze even the entire stationary distribution and not just the Q. Because you can have second moment, third moment, even the entire stationary distribution, and that's something that's interesting in real life as well, because you want to have service level guarantees. That you want to give service level guarantees that with a very high probability, 90% chance that your waiting time is not more than 20 minutes. To give such kind of guarantees, you would need to analyze more than the mean, the tails, even the entire distribution. So that's what we focus on in the second part of the talk. And to do that, we consider the canonical, the simpler setting where you just have a single type of customer and a single type of server. Now, even the simplest case is difficult to solve, because again, this can you can make connections of this with a single server queue. And even for a single server queue, it's still an open problem. For a GG1 queue, exactly what the stationary distribution is still an open problem. You only know it in asymptotic regimes. So even analyzing this would be challenging. So then the idea would be to consider some kind of an asymptotic regime. Again, heavy traffic, which is similar to a classical single server queue, where heavy traffic here would be defined as lambda, where lambda is the arrival rate of customer approaching the service rate mu. So you are pushing the system more and more towards heavy traffic. So something similar you might want to do.
So what do you mean the open problems in first someone one here?
For a GG1 queue, for a general traffic, general distribution of arrival, general distribution of service, under no asymptotic regime, what's the distribution?
Oh, it's not the matching at all. This is single view.
Single queue, yeah, just analyzing what the distribution of this is. So people know it only under heavy traffic asymptotic regimes, but not in general. Not generalized.
But even for MM1 is not.
MM1 is easy, right? MM1 is just a birth and death process.
In the control.
Right. Yeah. If you don't have a control, then that's very easy. If you have a control, then correct. Yeah, that's like some things are known. Like you can can write the stationary distribution. That's just going to be the product form of all the lambdas divided by all the views. So
That's for very special cases. Possibly static pricing.
no, even if you're so it's just going to be a birth and death process with state dependent.
It's both possibly different up and down transitions will be possibly.
Correct, but if it's just a single dimensional Markov chain, then you can write the stationary distribution, which would just be product of lambdas divided by product of views. I guess, yeah, sure. Okay, good. So under this setting, again, it's not clear what the heavy traffic definition would be. So here you can, because here it's like you don't have lambda approaching mu. It's not like lambda is less than mu, lambda is greater than mu. You have something that's state dependent. So again, what's the definition of heavy traffic? So here you can think of heavy traffic also as the system approaching null recurrence. Like when lambda is going to mu, you are pushing your system closer and closer towards null recurrence. And that's the intuition you want to use to again define what heavy traffic would be in this scenario. Again, let's consider the simplest setting of a two-price policy. So again, you have after a threshold, you reduce the customer arrival rate by a little, and similarly after a threshold. So essentially, if you are in this part, you have too many customers in the system, and if you are in this part, you have again too many servers in the system, and this is just the imbalance, which is number of customers minus number of servers. So again, this is the same two-price policy that we've seen till now for the single link two-sided queue. Now let's again consider the simplest case where again the arrivals are Bernoulli, so 0 or 1. That gives you just a simple birth and death process with again state dependent transitions. You go up depends on what your state is, and go down again with probability depending on what your current state is. Again, you can write the stationary distribution in a closed form. So again, there's nothing much to solve, because under this simplest case, you know what the stationary distribution looks like. But nonetheless, we do want to take a heavy traffic limit here to get intuition, and using that intuition, we can solve things that are more general than this specific scenario. So again, here there are two parameters. Epsilon is the magnitude scaling parameter, and tau is the time scaling parameter. And heavy traffic is essentially pushing the system towards null recurrence. That can be done by two ways, either by letting epsilon go to 0 or your threshold tau go to infinity. By doing that, you are approaching towards null recurrence, because again, you are approaching a static setting, and in a static setting when lambda equal to mu, you know that the system is null recurrent. Now, because you have two parameters here, that is going to the asymptotes. You have three different cases. Epsilon is going faster to its asymptote, or tau is going faster to its asymptote, or they are going to their asymptotes in a relatively similar fashion. Now, under these three cases, we are able to characterize. I mean, just take this limit under this condition. What you would see is the scaled imbalance would then converge in distribution to a Laplace distribution. And let me just show all the three cases. So essentially, to gain intuition, maybe let's start with the case 3. So here you can think of it as tau going to infinity, but epsilon being a constant. What that means is outside the thresholds, you have a very high drift that's putting your system between the thresholds. Inside the threshold, it really doesn't matter where you are. So what you see is a uniform between the threshold. Outside the threshold, you don't see any mass at all because there's a very high drift that puts you back into the threshold. So that's case 3 that you get uniform. In case 1, again for intuition, take tau being a constant and epsilon going to 0. That again looks very similar to a classical single server queue in heavy traffic. Again, that for that it's known that the limiting distribution is exponential for a single server queue. And here what you see is a Laplace distribution, which is just exponential on both sides. The reason being our state space is signed random variable, it can both be positive and negative. And finally, interestingly, what you see is that if it converges to some constant, then the scale imbalance would converge to something that's a combination of uniform and Laplace. So you would see Laplace tails and a uniform in between. So it's a nice phase transition, from Laplace to uniform through a hybrid distribution. Again, because this was the simplest case, you could do this by hand by just writing the stationary distribution and taking the limits. But again, the interesting thing here is that you can do the same thing, but with general control curves, general arrival rates, and general distribution of arrivals. But you don't have a birth and death process, but a general DTMC or a CTMC. And the good thing is that most of the things remain the same. So it does converge to a Laplace and a uniform distribution. The only thing that changes is that rather than a hybrid distribution, it converges to a Gibbs distribution, which depends specifically on what arrival rates you are setting. So again, the arrival rates are state dependent. Here it's not a two-price policy. Here it can be much more general than a two-price policy. It can be completely dynamic. Now, depending on what you are setting exactly, which depends on these certain curves, you get something that's a Gibbs distribution.
There is some condition on the side or 5 years for this.
Correct.
Like, at infinity and at 0.
Right. So few conditions. For this case, you only care about this at infinity. So you have some kind of a symmetry condition that the value, the difference of phi c and phi s at infinity and minus infinity is the same. The limits exist and they are the same. We also have a boundedness condition that both of them are bounded. Both of them.
And on the case 3 side.
Case 3 side, you have a monotonicity assumption. That phi c and phi s are monotonic. I think, these results, I think, is true even without the monotonic assumptions we need it for the analysis, but I think it should be true. Essentially, what monotonicity helps is that you get a single interval where phi c is equal to phi s, and that is the interval where you get the uniform distribution. If you don't have monotonic, then you can have multiple intervals, and then that's going to complicate your analysis.
How do you analyze? This is a normal process we are analyzing, right? Steady state distribution.
Yeah.
So what are the tools you're using?
Again, for this we are using transform method. So what we're doing is we are using some Lyapunov functions which relates to the transform the MGF of the imbalance, the variable z, setting its drift to 0 in steady state. That's going to give you some equation that involves the transform or some version of the transform. Then you take the limits, epsilon going to 0, tau going to infinity. That's going to give you an implicit equation in terms of the transform. By using some inverse Fourier transform, by doing some inverse Fourier transforms, we are able to essentially get a differential equation in terms of the PDF.
But your NGF or characteristic?
Characteristic. Because characteristic function can be thought of as a Fourier transform of the PDF. We get an implicit equation which involves the characteristic function. By taking the inverse Fourier transform, we get a an ODE in terms of we get an ODE in terms of the PDF of the imbalance, and by solving the ODE, you essentially get this stationary distribution. So the main idea is to use the right Lyapunov function, set its drift to 0 in steady state, and then eventually solve the equation that you get to eventually get the distribution of the impact.
You can generalize to more general process. This is kind of very specific, right? Okay, you cutting a base at two places.
Right, so this one is much more general because this one is not a two price policy. This one is 5C, and so this clause can be anything under some conditions. Correct, yeah. So general arrival range and the distribution, the arrival distribution is also general. Under these general settings, you can prove these results using transforms essentially. So again, I guess one advantage of this is you don't have to deal with any convergence to any processes and then analyze the process to get the stationary distribution, then show interchange of limits. Because first you take the limit in the process world, you first take the limit of epsilon tau going to infinity, you get a process, then analyze the stationary distribution, and then show interchange of limits, because you have to show interchange in terms of T and epsilon going to the asymptotes. So a lot of technical steps involved, but by doing the transform method, you are able to work with the original Markov chain directly and let T go to infinity first. So you get stationarity first, then let epsilon and tau go to infinity. So again, you don't need to show interchange of limits. You don't need to deal with the process level convergence, and essentially what you have is just some functional equations that you need to solve.
And this picture is a solution to only.
This one is solution to energy. Yeah.
So what is the distribution of India? So
This one is it gives which will be e to the power minus.
as in what is the x-axis?
Right. So the x-axis is going to be z, epsilon z or z over tau, the scale imbalance, and this is the PDF. Q, yeah, the balance of the Q.
Should tell people about transform method. Are they able to here about transform method?
Right.
You're upside.
Yeah. I guess I don't.
Is it analogous to usual like this? Like that? So if we're going to put central limits, there are many. I mean, like India, something has to match something. So one thing is characteristic function.
Correct.
So is this kind of thing?
Yeah. I mean that's analogous. That the way to prove central limit theorem is to.
So but like now you have this large distribution, and so what the
So the thing that changes in central limit theorem, you don't have the process.
here, yeah, it's a scale, but here it's here the convert, so the Laplace on Z is just so the single number still, right? So it's here.
Z is still a scalar.
Correct.
Z is the scalar, and then you look at the random variable that corresponds to the stationary distribution of Z,
Yeah.
and then you want to characterize the characteristic function of that random variable. So then what you want.
But there are two steady state. There are two things going to be infinity. One is the time, that is because of steady state,
Time,
and
correct.
then after that there is end.
Correct, exactly. So then what you want is to characterize the characteristic function of that random variable. The way to do it is to set the drift to 0. What drift essentially means is take any Lyapunov function.
Offset.
Take any as a function of Z.
But zero function is it's supposed to be decreased from another function.
The Lyapunov function, under like essentially the only condition you would need is the expectation under steady state of that Lyapunov function is fine.
Okay. But it has, so you're calling it Lyapunov, it has some kind of monotonicity for the Markov chain.
I don't really need to call it Lyapunov. Let's call it a test function.
Okay.
The only condition is the expectation under steady state is fine. Now once you have any such test function, what would be true in stationarity is the expectation of the test function at time k is same as the expectation of that at time k plus 1.
Yeah.
Stationarity. Now by using Q evolution equation, you can write what k plus 1 is in terms of k. So essentially that will give you an equation in terms of the random variable corresponds to the stationary distribution. And if you're lucky, you might be able to just take this limits epsilon and tau going to the asymptote.
This is what you're calling setting drift to 0.
Exactly, yeah.
That E of the
Exactly,
function.
Yeah, that's getting drift to 0. That gives you an equation in terms of
Distribution is the same, so it's not drifting. That time k and time k plus one
distribution is the same.
is the same.
Correct. Yeah.
you have a one-step relationship and they have the same distributions that is.
that has the same expectation, and by using the Q evaluation equation, you can write k plus 1 in terms of k. That gives you an equation in terms of the random variable that corresponds to the stationary distribution of Z. Now, if you are lucky, you can just take these limits epsilon going to 0 tau into infinity and get a closed form expression of the characteristic function of that random variable, and that's it, you're done. But what happens is, again, if you use it for a single subcube, it works out very, very nicely. You get exactly what the characteristic function is once you take the limits. And then you're,
Probably the implicit equation.
yeah, here you get implicit because of the state dependent.
So you have to argue what the solution is.
Yeah, you have to come up with a solution, show its uniqueness.
Yeah.
So coming up with a solution is not too hard because you can just plug in a few solutions and check, and then it works.
So you still get explicit solution. It's not like some implicit solution which shows unique just by showing some monotonicity somewhere. So you actually get a solution.
Yeah, because this is the solution, right?
Oh, okay, that's the
Once you put a distribution, you can show that it satisfies the equation. So you have existence, you know what a candidate solution is. Then the problem is how to show uniqueness.
Yeah.
And that's something that's like a big problem that's out there. But because it's a single dimensional process, it's not too hard. Essentially, what we use is some ideas from inverse Fourier transform. By interpreting that the characteristic function is same as the Fourier transform of a PDF.
So, but that's like saying that under reasonable conditions, the characteristic function more or less characterizes the distribution. So the form, then, yeah.
Yeah, but because you have implicit equation, you're not able to get a closed form expression of the characteristic function itself. And that's why the whole problem appears as to now you want to solve this implicit equation that involves characteristic function and something that relates to characteristic function. But because it's a functional equation, you don't know if it has a unique solution. So the way we do it is by doing this inverse Fourier transforms. That gives you an ODE in terms of PDF. Again, this is very hand wavy because you don't know
But
the
this
PDF.
functional equation is not like it's a single point, like it's a differential equation.
It's a differential equation. You know, the functional equation is the equation that relates, that has this Z bar in it, expectation of Z bar.
Oh, but then some it's like a time delayed differential equation.
No, because we were able to set Z k plus 1 in terms of Z k. So there's no time anymore, but there's just expectation and Z bar. That's in there, right? And then right, so that's what you have. If you take inverse, then this characteristic function essentially becomes a PDF by taking inverse Fourier transform. And if you have like the exponent in multiply to it, then that becomes a derivative, right? As the Fourier transform. So then that gives you an ODE. But again, this is very hand wavy because you need to know if the PDF exists, if it's differentiable, etc., etc. So to formalize this, again, we use temper distribution, which is the dual of short space, that generalizes the definition of a function. And then everything is well defined, and then you can go from there. So essentially, everything that I've said essentially holds true. You just need to use some machining, and that works out essentially. So again, in most of the cases, the transform methodology stays the same. That you set the drift to 0 of some Lyapunov function, test function. You need to be careful what test function you pick because that's going to give you different equations. Once you have an equation, you take these limits of whatever quantity that you have. That's gonna either give you an explicit equation, an implicit equation, or maybe a differential equation in terms of the characteristic function. If you have abandonment, you do get a differential equation in terms of the MGF itself. That's different from the differential equation here. So then the last part is something that's tailored to the problem itself, because the equation that you get, you will need to solve it based on what equation you get. But the 3 steps always remain the same. Set the drift to 0, take the limits, and solve it. Again, the advantages are no process level convergence, no interchange of limits. You don't have to work with all the technicalities. It's still very powerful.
You need to know what is working towards. I mean, if you don't know
yeah, you don't need to know that as well. That's true. But it does help because by knowing what the answer is, you can pick the Lyapunov function. And that's essentially what I did actually. By knowing these, you pick the Lyapunov, because what you're expecting at the end is the characteristic function of a uniform distribution. So you pick your Lyapunov function in such a way that you end up with the characteristic function of the uniform distribution. So that does help you to reverse engineer the Lyapunov function you want to use. But again, the key to all of this is to come with the right diagonal or the test function. Once you have the right test function, everything is easy. You just do algebra, take some limits, just be a little careful with the machinery, but it's pretty elementary overall compared to process level conversion. That's the advantage of sorry, we went on a big tangent.
That's the last slide.
Yeah, this is the last. I mean, essentially, this is the last slide in this part. I can just end with we have some extension in terms of strategic servers that a server arrives, it can see prices of all types of queues, and then it may decide to join some other queue if the price is higher. Under this strategic setting, again, we are able to show again incentive compatible, near optimal pricing and matching policies for again wide variety of utility functions, because depending on the utility functions, the servers are going to behave differently. And finally, another work that relates to these matching queues is again electric vehicle infrastructure planning. So the question that we are asking is for a given arrival rate of riders, how many EVs and chargers are required to achieve a desired service level? That's again like a capacity planning problem. Again, we're not going to put the details, and that's it. Thanks. Questions?
No, thanks.
Thanks.
Thanks.